So in these notes, we're going to be looking at equilateral and isosceles triangles specifically. So we're going to be able to prove theorems about isosceles and equilateral triangles. These relationships are going to be useful in a lot of different things that we do in later units. Once we know things about isosceles, we can use it to make other relationships later in geometry. And then you have it when you can apply equilateral triangle theorem or the isosceles triangle theorem, which we'll get to in just a moment. So first, let's look at equilateral. Equilateral triangles are all equal. That's why they're equilateral triangles. All three sides are congruent. All three sides. They're all the exact same length. They're all congruent. So what that's going to look like is you'll see a picture of a triangle kind of like this, and it will have a tick mark, the same tick mark on all three sides to show that they are congruent, that they're exactly the same. Now, the equilateral triangle theorem says that if all the sides are congruent, so if it's an equilateral triangle and all three sides are congruent, then the angles are also all congruent. So if the three sides are congruent, then the three angles are also congruent. So that should make pretty good sense if you just think about rotating this triangle. If you rotate it, all the angles match up when you rotate it one time. If you rotate it again, they all match up again. It has rotational symmetry, which means all the angles have to be congruent because now we've matched up E with all of them, we've matched up D with all of them, we've matched up F with all of them. All the angles have to be congruent because it has rotational symmetry. So that actually works both ways. If the three sides are congruent, then angle D is congruent to angle E is congruent to angle F. If the three sides are congruent, then the three angles are congruent. And then the converse is also true. If the three angles are congruent, then those three sides are congruent. So if the sides are congruent, the angles are congruent. If the angles are congruent, then all the sides are congruent. So another piece that we can add to this is if all three angles are the same, if they're all congruent, all three sides are the same, all three angles are the same, we know that those three angles have to add up to equal 180 because it's a triangle. And they're all the same. So if they're all the same and they add up to be 180, there's only one number that they could be. 60. All three angles of an equilateral triangle will always be 60 degrees. It's the only thing they can be. They have to add to be 180. They have to be the same thing. 60 is the only number that's 60 plus 60 plus 60 equals 180. That's it. So there's a couple markings that you might see. You could see that all three sides are congruent, which would tell you all three angles are congruent, or vice versa. If all three angles are congruent, then you know all three sides are congruent. And then the third thing that you would know about that is not only are they all congruent, they're all 60. They're all 60. All the sides are the same. In fact, if two of them are 60, the third one has to be 60. So if you know two of them are 60, the only thing that third angle could be is 60, because that's the way it has to add up to be 180. The three angles always equal 180. So if you see 60s in the triangle, you know what triangle it's going to be. So an isosceles triangle, it's almost as cool, but instead of 3 congruent sides, it has 2 congruent sides. So 2 sides are exactly the same. The third side, the one that's different, you call that the base. So the different side is called the base. The 2 sides that are the same are called legs. So you have the 2 congruent legs, then you have the 1 different base. And then the one between the vertex is called the angle between the 2 legs is called the vertex. So here's a leg, here's a leg. They are congruent. This angle right here is called the vertex. Angle. This side down here is called the base. It's the different side. And then these 2 angles down here are called the base angles. So you've got 2 legs in the vertex angle, and then you've got the base with the 2 base angles. So we're going to do a construction. We're going to construct the perpendicular bisector. This segment down here, AC. We're going to construct the perpendicular bisector. So perpendicular bisector, that's the one where kind of makes that football shape. So we're going to take our compass from one endpoint, from A, stretch it more than halfway, and then draw the big arc, like half of a circle. And then without adjusting your compass at all, move it over to the other endpoint, C, and do the exact same arc. So you can get that football type shape. So your perpendicular bisector connects the top of that football to the bottom of the football. That's your perpendicular bisector. Just use your straight edge to draw it out. So they want us to name this BD. So right here we can put B and then D. And now it asks the question, is ABC an isosceles triangle? So if it's an isosceles triangle, that means that two sides are congruent. So we're checking to see is AB the same length as AC? Now you could have drawn B wherever you wanted to. You could have put B right there. It won't matter. So stretch it out with your compass. Oh, that's like exactly as far as I can stretch. That's how long AB is. Is BC the exact same? So mark it over, check it out. Yep. The bottom is longer though. AC is a little bit longer the way I drew it. Maybe your AC is a little bit smaller. I don't know. But these two sides are congruent. We just measured them with our compass. We stretched it out. They're the same length. So is it isosceles? Yes. This is how you construct an isosceles triangle. So this triangle, no matter where we put it, I don't know if I'm going to be able to do this. No matter where we put B on this perpendicular bisector that we drew. If we drew it here, that's still going to be isosceles. You can measure those two sides. It's still going to be isosceles. No matter where we draw it on that shape, on that perpendicular bisector, no matter where it goes on this line, it's going to make an isosceles triangle. You can pick wherever you want, but it's going to be isosceles, no matter what. If you put it down low, up high, it's still going to be isosceles. Even if you went kind of way different and drew it down here on the bottom, then I would still make an isosceles triangle. It would just be kind of upside down from what you're used to. So that actually leads us to this theorem right here, the perpendicular bisector theorem. A point is on the perpendicular bisector if and only if it's equidistant from the endpoints of the segment. So if it's a perpendicular bisector means you get the two tick marks, the two congruent sides, and a right angle. No matter what point you pick, if you pick H or G or F or E or even C, they're going to be the same distance. You're always going to get an isosceles triangle this way. If you pick this one, those are going to be the same distance. If you pick this one, those will be the same distance, the same lengths. Or even if you did this one, those sides will be the same length or the same distance. It's pretty easy to see that you could fold along that perpendicular bisector right there. You could fold it in half and get reflexive, or a reflection, not reflexive. You can get a reflection. You can see that they are the same. So we're going to take that construction we just did, construct the perpendicular bisector, so when you've got the construction, we know BD is the perpendicular bisector because we made it that way. You know things that you create that way. So BD is a perpendicular bisector. What does that mean? So there's two words there that you can define. perpendicular, and bisector. So perpendicular means you get right angles right there, which means they're congruent because all right angles are congruent. Bisector means it cuts it in half. So it's cutting AC in half. So you get those congruent sides right there. Now, also from this picture, we know we've got reflexive. We know we've got the reflexive side right here. BD is part of both of those triangles. So we've got three congruent parts, which means we've got enough to decide why these triangles are congruent. We've got two sides, the angles in between, that's side, angle, side. So identify what we've got real quick. We've got our sides, AD, congruent to CD. We got the angle, BDA, congruent to BDC, or you could have flipped those letters around, that's okay too. CDB and ADB, that would work too. And then we've got the reflexive side right here, BD, congruent to itself, BD. So there's our side, angle, and side. So that's what we're going to have to put into our proof with the reasons. So we've got it's a perpendicular bisector. Since it's the perpendicular bisector, this one goes a little bit different. We can also use this perpendicular bisector theorem we just said. Makes sense. If we use that, that's going to jump and tell us that the two sides, the two legs, are congruent. So change that around. There's more than one right answer, more than one right proof. From that theorem we just used, we got the perpendicular bisector theorem. Those two sides are congruent. Which means it's isosceles because those two sides are congruent. Since it's isosceles, or before that, AD is congruent to CD. My bad. We marked that one before. And we also still know the reflexive side. So the only thing we did is we changed out the right angles here, changed it out for the perpendicular bisector theorem to say, instead of the angles, you could say that those sides. Either way is okay. You either do side, angle, side like we wrote down originally, or now we've said all three sides are congruent, which would be side, side, side. Whichever way you like to prove it, it's fine. But if you're going this way, you have to remember perpendicular bisector theorem. If you go the other way, you just have to remember right angles are congruent. So that's not what it asked us to prove. It did not say prove the triangles are congruent. It said prove A is congruent to C. Those are corresponding parts, though. They match up. If you reflect these to make them match up, they're corresponding parts, which means they will be congruent. So either way would be okay. You could do a side, side, side. You can also do a side, angle, side, the way we decided to write it out. So what that just proved by doing it this way, either way you would have proved it. We know it's an isosceles triangle because these sides were congruent. And we just proved that those angles are congruent. That's actually a theorem called the Isosceles Triangle Theorem. If two sides are congruent, then those the two angles that are opposite are also congruent. If AC is congruent to AT, then angle C is congruent to angle T. So if the legs are congruent for an isosceles triangle, then the base angles are congruent. And it works the other way also. The converse is also true if you flip it around. If you know angle C and T are congruent, then you can know that the sides are congruent. Works either way. If you know the sides, you know the angles. If you know the angles, you know the sides. So one more thing about isosceles triangles with the perpendicular bisector drawn in. That perpendicular bisector will also always bisect the angle up top. The vertex angle. That perpendicular bisector down the middle splits it into two congruent triangles. So everything on each half will be congruent. It's kind of a good way to think about it. It splits the isosceles triangle in half. So we know those sides are congruent, but it also makes the base angles congruent and the vertex angles congruent. Because it's the reflection over that perpendicular bisector. Everything matches up. So for this example, we're going to look at what we're told. DEF congruent to DFE. These angles are congruent, which ties to a theorem we went over today. When the two angles are congruent, that means the sides that are across from those are congruent. It's the isosceles triangle theorem. Since we know the two angles, that means we know those two sides. So now we're going to use that theorem, that property. EF is 2x plus 7, down here at the bottom. DF is 4x plus 3. And DE is 6x minus 5. Now, it's saying find the perimeter. We can't find the perimeter until we know x. But we can find x because we know these two sides are congruent. If they're congruent, that means they're equal. So that means 6x minus 5 is equal to 4x plus 3. Now we're going to solve for x. Once we know x, we can find the perimeter. So get your x's together. Add 5 to both sides. 2x equals 8. And then that means x divided by 2, you get x equals 4. So if x is 4, now we can figure out what all three sides are by plugging in 4. So we got 6 times 4, 24, minus 5, 19. X is 4, plug it in. 4 times 4 is 16, plus 3 is 19, which is good. Those were supposed to be the same. That makes sense. X is 4, so this is 2 times 4 is 8, plus 7 is 15. So the perimeter, you add them all up. Add up all 3 side lengths. 19 plus 19 plus 15. All right, let's fix that 15 real quick. 19 plus 19 is 38. Plus 15, 53. So the perimeter is 53. Here we're going to use a slightly different theorem we just learned about, different property we just learned about. It's an isosceles triangle with base BC. If it's isosceles, that means the base angles are congruent. So if BC is the base, that means angle B and angle C are those base angles, because these would be the 2 sides then. So those 2 base angles are the same. So that means 6x minus 2 equals 8. Uh-oh, that's a y. That doesn't help us out. You can't solve when you have an x and a y. So we're going to do something different. We're going to, for just a minute, pretend they didn't even give that to you, because right now that is not helpful at all. Just for a minute, because we're going to need to bring it back in a little while. So since it's isosceles, though, that means these 2 are the same. So if this one is this weird 6x minus 2, this angle over here is also 6x minus 2. Because they have to be the same because it's an isosceles. The base angles are exactly the same. So now that helps a little bit, except it wouldn't make sense to say 6x minus 2 equals 6x minus 2. You can't solve anything from that. You get 0 equals 0, and it doesn't work. But we do know all 3 angles now. We know something about all 3 angles. We can say 6x minus 2 plus 13x minus, or plus 9, equal, or plus 6x minus 2, it's a mouthful, all 3 angles adds to 180. All 3 angles, 6x minus 2 plus 13x plus 9 plus 6x minus 2. That's all 3 angles, and every triangle, whether it's isosceles or not, every triangle, the 3 angles add to 180. Now we can at least figure out what x is, and then we'll worry about y after that. So combine all your like terms here. 13x, 6x, and 6x. 25x. Negative 2 plus 9 minus 2. 7 minus 2 is 5. And to finish it off, we're going to subtract the 5. Divide by 25. X is 7. So we found the value of x. X is 7. Now we got to go back to the first thing that we wanted to say. These two angles, 6x minus 2 and 8y minus 8, they're equal. So 6x minus 2 is equal to 8y minus 8. And then the only way that this becomes solvable is because we know x is 7. X is 7, so plug that in. 6 times 7 is 42, minus 2 equals 8y minus 8. So that's 40 equals 8y minus 8. Add the 8 over, you get 48 is 8y, and then divide, you get y equals 6. That's a pretty long problem, a little bit challenging because you had to first remember to ignore what they told you, solve for x, and then go back, solve for y.